Welcome friends, we are discussing network theory. In the past few modules, we have discussed different aspects of network theory. In the last module, we have started solving different network techniques like KCL, KVL. Then we have seen different theorems and we have solved different problems on them. Now, in this module, it is an extension of the previous module. We shall solve more problems on network solving techniques that we have discussed in the previous module. We have discussed Thevenin's theorem, we have discussed Norton's theorem, superposition theorem, maximum power transfer theorem, then nodal analysis, mesh analysis. And in the past module, we have only considered the DC network. Now in this module, we shall consider slightly higher version of such networks with dependent source and of course with the AC networks. Now with the incorporation of the dependent source, the network will behave differently. So we shall see the steps to find current flowing through any branch or potential drop across any branch when of a network, when that network consists a dependent source. So we shall see the steps. So we shall see many problems on different techniques. So let us start one by one. So for the first few problems, we shall consider theorems, that is Thevenin's theorem. So there are three fundamental steps we have understood or we have seen for a problem of Thevenin's theorem. We need to first find out Thevenin equivalent voltage, which is equal to E Thevenin, which is called E Thevenin. Thereafter, we shall evaluate the Thevenin equivalent resistance, which is called R Thevenin. And from these two, we shall construct Thevenin equivalent network from where you will get the current by this formula ETH, that is the Thevenin voltage divided by Thevenin resistance divided by load resistance. So these are the three fundamental steps of Thevenin's theorem. Now in this module, we shall discuss our first problem, that is shown in figure 1. So we have a simple DC source of 2 volt and we have a dependent source. Now the problem with this dependent source is that its magnitude is dependent on some other parameter of the network. Just for an example, this is a current source. This is a current source. By this arrow, we can understand this is a current source. However, this magnitude of this current source is dependent on the voltage of this V0. That means whatever voltage is appearing across these 10 ohm resistors, that is effectively determines the magnitude of this dependent current source. So that is the peculiar nature of dependent sources. So if a network encounters a dependent sources like that, then how to solve this problem? So now we shall proceed step by step. Now let us first make this 10 ohm, that is our step 1 for us. We need to remove 10 ohm by open circuiting it. So first step, it involves, let us open circuit our 10 ohm resistor. Let us open circuit our 10 ohm resistors and to find out ETH. That is the open circuit voltage across the 10 ohm resistor. So we have the 10 ohm resistors connected across these 2 points. Let us say these points is 1 and 2. So let us open circuit the 10 ohm resistor, this 1 and 2, and this voltage appearing across this volt or terminal 1 and 2 is ETH. So now, just if you compare with the previous diagram, that is figure 1, that voltage appearing across 10 ohm is V0, voltage appearing across 10 ohm is V0. From there, the magnitude of the current source was 2 V0. So, if you consider figure 1, now as you remove the 10 ohm resistance, then the open circuit voltage is E Thevenin across the terminal 1 and 2. Therefore, the magnitude of current sources becomes 2 ETH right now. Now, so with comparison to figure 1 and figure 1a, initially the magnitude of the current source was 2 V0, because V0 is the voltage appearing across 10 ohm resistor. So whatever be the voltage across the 10 ohm resistors, it will be double. The current magnitude is the double of that. So using this logic, open circuited terminal, we have the voltage E Thevenin, that is open circuit voltage. So the magnitude of the current source become 2 ETH. And no current should be flowing through this 3 ohm resistor, because it is an open circuited path. So effectively what we have here is that we have this 2 volt source. Then we have a series resistance of 5 ohm. And then we have a current source, dependent current source. Its magnitude is 2 ETH. And after that we have, of course, this 3 ohm resistor. However, this is open circuited terminal 1 and 2. So no current should be flowing through this. It should not be flowing. Any current should not be flowing through this. And this voltage is ETH. So as this open circuited terminal is ETH, so we can write the KVL equation of this mesh. So by analyzing this mesh, we can understand that here is the only current source is 2 ETH. So the current must be flowing to ETH. That is the current magnitude. So if we write the KVL equation, now let us mark the polarity. Since current is flowing in this particular direction, then the polarity of the potential is this, plus minus, and of course this ETH will be falling across this terminal. See, this ETH, that is open circuit voltage, that is Thevenin voltage, will be appearing across these 2 terminals. Let us say this terminal X, let us say this terminal Y. So we can write V12 is nothing but ETH. Which is also equal to Vxy, because it is falling directly on XY. Okay, so we can write the KVL equation as, you see, this is minus plus, and these two are 5, the voltage drop across 5 ohm resistor, it is plus minus. So this voltage drop across 5 ohm resistor is 5 into 2 ETH, because this is the current flowing, 2 ETH is the current flowing, and rest is the ETH is the Thevenin voltage. So these two voltages are in series, that means they are additive polarity, and with respect to this 2 volt source is subtractive one. So we can write 2 is equal to 5 into 2 ETH plus ETH. So if you solve, so we can get ETH is equal to 2 by 11 volt. ETH is equal to 2 by 11 volt. That is our solution, first solution for us. So open circuit voltage we got is 2 by 11 volt. So ETH is equal to 2 by 11 volt. So let us proceed the second step, which is to find out RTH. Now, if we follow the conventional method that was discussed in the previous module, that method will not work here because of this dependent source. Because if we try to calculate the resistance, equivalent resistance of the network, this dependent source will create problem because we do not know the resistance of this current source. We do not know. The answer is quite simple. We do not know resistance of the dependent current source. So the method that was discussed in the previous module, that will not work here. Now to solve this, we should apply some different or some alternative approach to evaluate RTH. So what we do here is that we connect additional voltage source, which is EDC. Let us connect a battery of EDC, right? That will inject a current of IDC. So what should be the approach? A battery is connected across open circuited terminal, that battery voltage is EDC. Okay, now that the battery will inject a current IDC. That battery will inject a current IDC. So our RTH, that is Thevenin equivalent resistance, is nothing but the ratio between EDC by IDC. So if you can evaluate EDC by RDC, that will be the RTH for us. So this is our alternative approach. So we must connect a battery of magnitude EDC that will inject a current of IDC. So when you evaluate EDC by IDC, that means this ratio, that is nothing but actually Thevenin equivalent resistance for us. Now in some alternative approach, or maybe you can say alternative opinion, is that instead of adding a battery magnitude EDC, simply 1 volt source is connected. 1 volt source is connected and that injects a current IDC. This is an alternative approach. Or let us say alternative opinion. Instead of having EDC, let us connect a battery of voltage 1 volt that will inject a current of IDC. So when you calculate or when you evaluate 1 by IDC, that will be giving nothing but the equivalent resistance of the network, which is called Thevenin equivalent resistance. So here they are doing nothing but they are considering EDC is equal to 1 volt. EDC equal to 1 volt. Both approaches are same, but here they are, in this second opinion, they are specifically mentioned EDC is equal to 1 volt. Simple as that. So both approaches are same. So here in the entire problem, I have considered the EDC. Now it is up to the you which option you will follow. Whether you consider EDC or whether you consider 1 volt, it's all the same. You need to write KVL equation appropriately. So now if you consider this diagram or this network, let me draw it again. Let us say this is 5 ohm resistor Then we have a 3 ohm resistor. Then we have a battery of EDC. And this voltage source is short circuited, right? This is short circuited. And this terminal is X. So this is actually that current source. Now this is EDC. It is connected across the terminal 1 and 2, which is injecting a current IDC. So according the rule of this current source, dependent current source, now this current magnitude will be times EDC. This current magnitude becomes 2 times EDC. So if you now evaluate the KCL at node X, if you now try to write KCL at node X, so we have 3 currents. First current is IDC, which is entering to the node X, which is IDC, that is injected by that voltage source. IDC is injected by that voltage source. And there are 2 more currents, that one current is leaving in this direction, one current is leaving in this direction, which is EDC, which is 2 EDC rather, in this direction, this current. And however, there are another current which is flowing through this 5 ohm resistor, which is nothing but Vx by 5, because this voltage, this potential of this node X is Vx. So this current is Vx by 5. Actually, this current is Vx by 5, that is written. So there are 2 outgoing currents. One outgoing currents. So first outgoing current is 2 EDC. This is number 1, this current. And second outgoing current is this one, that is Vx by 5. Now, which must be equal to incoming current, which is IDC. Now, what is actually IDC here? Now, IDC becomes, what is IDC? IDC becomes, you see, this node potential is Vx, this is EDC, so basically the IDC is flowing due to the potential difference between these two. So IDC is basically EDC minus Vx divided by 3, because that current is flowing through this 3 ohm resistor. So that is the exactly thing it is written. X by 3 is equal to IDC. EDC minus Vx by 3 is equal to IDC. So from this equation, if you solve, so 2 EDC plus, now what is Vx? Now what is Vx? Vx is equal to nothing but 3 IDC, or rather, sorry, it is actually EDC minus 3 IDC from this equation. So this we are getting from this equation. So Vx is equal to nothing but 3 IDC, EDC minus 3 IDC. So that divided by 5, because we have Vx by 5, that is equal to IDC. So if you solve this, so then you will get EDC by IDC, if you solve, which is equal to RTH, that is equal to 8 by 11 ohm. So the entire solution is solved here. So that is exactly written IDC is equal to 2 EDC plus EDC minus 3 IDC by 5. If you solve, you will get RTH is equal to EDC by IDC, which is equal to 8 by 11 ohm. So the third step is pretty simple and straightforward. We must construct the Thevenin equivalent network. What is Thevenin equivalent network? We must connect E Thevenin, RTH and RL. Which is RL? What is RL? Here it is, we have 10 ohm. We have 10 ohm. That is our RL. So if you solve this, then current flowing through there, that will be EDC, which is equal to 2 by 11 EDC by RTH by RL. So EDC is equal to 2 by 11, RTH is equal to 8 by 11 plus 10. So if you solve this, you will get 1 by 59 ampere current. So the current flowing through, the answer will be the current flowing through 10 ohm resistor is equal to 1 by 59 ampere current. So the overall method is quite similar that we have discussed in the previous module. Unlike the RTH solution, to solve the RTH, we must connect a battery. We must connect a battery source of magnitude, known magnitude EDC, or it may be some other value as well, which should connect or which should inject a current IDC. So the ratio between EDC and IDC essentially depicts the magnitude of RTH. So that is the process of calculating RTH when we encounter a dependent source in the network. So this is the standard process. So let us move to our next problem. Again, we have a problem with Thevenin theorem, that in the figure 2 we have some different circuit. Now it is to determine the current flowing through 1 ohm resistor. So this is the 1 ohm resistor. So here it is our load resistance for us in this problem, RL. So let us solve one by one. Now again, in this problem we encounter a voltage source, dependent voltage source, that is dependent on this magnitude V0. It is 2 V0 actually, the magnitude of the voltage, dependent voltage source, right? So we have the 3 steps just we have discussed for the previous problem. Now let us first do one by one. Now let us first solve the first step, which is evaluate open circuit 1 ohm resistance and to calculate ETH. To calculate ETH, right? So let us do that. So this 1 ohm resistance is removed and the terminal is open circuited. Let us say that terminal is 1 and 2. Let that 2 terminals are open circuited by removing 1 ohm resistance, and this voltage is ETH. So now if you analyze this circuit, so no current should not be flowing through this mesh actually. Through this mesh, no current should be flowing because it is open circuit terminal. Hence, this 5 ampere current is entirely flowing through this 2 ohm resistor. 5 ampere current is entirely flowing through this 2 ohm resistor. So from this diagram, we can directly write V0 is equal to 5 into 2, which is equal to 10 volt. Is equal to 10 volt. So this voltage is equal to 10, right? So the dependent source value is 20 volt as shown in this diagram. So V0 as we calculate, it is equal to 10 volt. So dependent source is 20 volt. So now if you apply the KVL, Now if you apply the KVL, now let us check the polarity of individual potential. So the initial source polarity is having plus minus like this. Now ETH having the left side plus, right side minus, so it is subtractive to the 10 volt source. So we can write 10 minus ETH. Now with respect to ETH, again this 2V0 is subtractive. So this 2V0, that 20 volt, is additive with this 10 volt, because minus plus, though these polarities are additive, so we can write 20. Again with respect to this 20 volt, again this 10 volt, that is the voltage drop across this 2 ohm resistance, this is plus, this is minus, so this is subtractive polarity with respect to 2V0, because 2 plus polarities are face to face, okay, that is why they are subtractive. So one should take a minus sign of 10 volt, so that is equal to 0. So we can directly write from here ETH is equal to 20 volt. ETH is equal to volt. So there are gist to understand this KVL. Once again, there are two additive polarities like 10 volt and this 20 volt, because they are additive. This 10 volt source, this one, and this 20 volt dependent source. And there are two more subtractive polarity, which is ETH and this 10 volt, which is appearing across 2 ohm resistor. So they are, since they are exactly opposite to each other, they must be equal. So from this equation we can write ETH is equal to 20 volt. Okay. So now let us solve the second part, which is RTH. Now what is the standard process to measure RTH? First we need to connect a battery of known magnitude, which is EDC, and you must inject a current, that battery must inject a current which is equal to IDC. Okay. And one condition is added, or it is must, that we, whatever voltage source and current source we have, we must remove all those three, all those sources. So there was a 10 volt battery here at this place. So 10 volt source is removed by short circuiting those terminals, and here we had 5 ampere current source. Here we had 5 ampere current source. We removed 5 ampere current source by open circuiting this. Right. So just now you can understand, now if you analyze this circuit, then this IDC amount of current, is flowing through this mesh, the mesh number 1, as it is indicated. So now if we can directly write down the KVL equation, so let us check the polarity first. So EDC, the battery polarity is left side is plus, right side is minus, and the dependent source is, this is minus, right hand side is plus. So these two are subtractive polarity. So we can write EDC minus 2V0, and now this IDC is flowing in this direction. IDC is flowing in this direction. However, initially we have chosen the polarity to be like this. So this V0 we can write, because initially we have assumed the V0 polarity to be like this. The upper node is plus, lower node is minus, and depending on this polarity, the polarity of the dependent source is this. Okay, so you cannot change the polarity of V0, as because the current is flowing from bottom to top. as per this convention you cannot alter, because initially you have chosen the polarity of the 2 ohm resistor is plus minus, upper node is plus, bottom node is minus. Because of this the polarity of the dependent source is like this, right? So you cannot alter this, okay? Even if the current is flowing in this direction, even if the current is flowing in this direction, which is IDC, you cannot change. So you need to incorporate this phenomena, in your KVL equation. So if you understand, again I am writing the KVL equation for you. So there are, let me first figure out how many potentials are existing. So first potential is EDC. So EDC is one potential. Then we have 2V0. Then we have 2V0, right? And third one we have V0. There are three potentials, right? Now let us figure out which one additive. You see the polarity of EDC and V0 are additive because plus minus. So these two are additive. So we can write EDC plus V0, and with that 2V0 is subtractive. So we can write 2 minus 2V0, that is equal to 0. So EDC that will be is equal to it is 2V0. So EDC is equal to V0, right? Now what is V0? Actually V0 is nothing but minus 2 IDC. V0 is nothing but minus 2 IDC because of this polarity. So with this, from this equation we can write the ratio, if you only consider the ratio EDC by IDC, which is equal to 2 ohm. So from this equation EDC is equal to minus 2 IDC. So from here if you solve this, EDC by IDC, which is RTH, which is equal to 2 ohm. So now step 3 is nothing but to construct Thevenin equivalent resistance, which is equal to ETH, RTH, then RL, which is equal to 1 ohm. So ETH we have solved equal to 20 volt. So ETH we solved equal to 20 volt. RTH we solved equal to 2 ohm, and RL we have 1 ohm. So answer will be 20 by 3 ampere. So the current flowing through this 1 ohm resistance, is 20 by 3 ampere. And the direction, you must consider the direction is this. Direction is this. Okay, let us proceed to our next problem. So problem number 3, what we have now, it is a AC source. Now in this case we don't have only resistance, but in this case we have a impedance. So we have two sources, one is voltage source 20 angle 0 volt, and another one is current source 5 angle 0 ampere current. Now we need to find out the current flowing through 5 ohm resistance. So this resistance you need to consider as RL. So you need to calculate the current flowing through. Now this reactance of J4 ohm, that will make the problem little bit lengthier. because this will incorporate, or that this will induce the impedance part of it. Okay, so let us solve one by one. So let us first open circuit the 5 ohm resistance. So let us, this is ETH. So now if you solve this problem, so if you analyze this, so no current should be flowing through this open circuited terminal. So this 20 volt source will inject some current through 5 ohm resistance, and this current source will inject its current. Okay, now these two currents will flow through this 10 plus J4 impedance. So this impedance, it is representing actually a impedance. Okay, this actually representing a impedance which is equal to 10 plus J4, because they are connected in series. So now as this, if you consider this node as Vx and this node is Vy, X and Y, two nodes. So and since this EDC is directly in parallel to this X and Y node, so we can directly write this, whatever is Vxy is nothing but ETH, because it is directly parallel to each other. Nothing is between, no resistance or no reactance is connected in between. So whatever voltage appearing across X and Y, which is Vxy, is nothing but that is ETH. So now what is KCL at node X? Now this current is nothing but 20 minus Vx by 5. 20 minus Vx by 5, that is written. Now again, what is Vxy? Vxy is equal to ETH. So this Vx can be substituted by ETH. That is number 1. Now to this node X, another current is entering which is equal to 5 ampere. So that is why it is written plus 5. And to this node X, from this node X, one current is leaving, which is current flowing through this 10 plus J4, which is nothing but ETH by 10 plus J4. ETH by 10 plus J4. So we can write again at node X, we have this current is equal to 10 minus ETH by 5. This current again is 5 ampere, and this current leaving through this reactance is ETH by 10 plus J4. So now if you solve this entire equation, so you will get ETH is equal to 31.25 volt but an angle of minus 6.9 degree. So this is your ETH. So your ETH is equal to 31.25 at an angle of 6.9 degree. This is your ETH. Just you need to solve this equation. This 10 plus J4 is converted to its complex conjugate by multiplying its complex conjugate by in the numerator and denominator 10 plus J4 into 10 minus J4. So the denominator part will become 116. And then if you solve step by step, we will get this answer. Now secondly, let us proceed to our second step, which is evaluating ZTH. Now in this case it is not RTH but it is a ZTH, because it is a AC circuit. We have an impedance. Now first we need to remove this voltage source by short circuiting this terminal, and you need to remove that remove this current source by open circuiting this terminal. So basically these two terminals are short circuited and these two terminals are open circuited by after removing the voltage sources. So with respect to these two terminals ZTH, basically there are two different paths. One is along this 5 ohm resistance and another one is along this 10 plus J4. So basically ZTH is nothing but 5 ohm parallel with 10 plus J4 impedance. So that is the thing. There are actually two paths. One is 5 ohm, another one is this reactance. So basically these two are parallel paths. So 5 ohm and 10 plus J4 are parallel. So if you solve this, 5 into 10 plus J4 divided by 5 plus 10 plus J4, if you solve this, you will get 3.47 at an angle of 7 degree. Now the third step, represent Thevenin equivalent network. That is the Thevenin equivalent network, which is ETH is equal to 31.25 at an angle 6.9 degree. ZTH is equal to 3.47 at an angle of 7 degree, and RL is equal to 5 ohm. Now if you solve this, you will get 3.7 at an angle of 4. Now how you can solve? The numerator is 31.25 at an angle of 6.9 degree. Denominator will become now 3.47 angle 7 degree. If you expand this, it will become 3.47 cos 7 degree. This is the real part. Now you should incorporate this 5 with this because they are real. Now the sine part, the sine component is the imaginary part, 3.47 sine 7 degree. So now if you solve this and divide these two polar form, you will get 3.7 at an angle of 4 degree. So that is the current flowing through this, this 1 ohm or rather 5 ohm resistance. This current actually, it is solved. Now one important observation here is that since it is a AC network, we can estimate or we can observe that for maximum power transfer, what should be the value of RTH. So if your RL is purely resistive, right, consider ZTH. Having said that, let me first note down what value of ZTH we have calculated. We have calculated 3.47 angle 7 degree. So if we have the type of load, this is a pure resistive load, then that value must be equal to 3.47 ohm. Just this value we need to have the maximum power transfer, because our load is purely resistive one. Now if the load is purely reactive or impedance, we have the impedance load, variable impedance load, then that value must be equal to 3.47, it must be complex conjugate, minus 7 degree. So if you solve, you will get 3.44 minus J.42 ohm. So for maximum power transfer, if we have a resistive load, then that value must be equal to 3.47 ohm. And then if we have a impedance load, then that value should be this one, that is 3.44 minus J.42 ohm. So let us proceed to our fourth problem. Now similar problem with a dependent source. Find the value of RL so that maximum power can be transferred to the RL. So this is RL. Okay, so you need to evaluate the value of RL so that maximum power can be transferred. So this problem is basically to evaluate RTH, because we know for the resistive load and DC circuit, if we meet this condition, and RTH is equal to RL, then we can say that maximum power should be converted or should be transferred from the source to the load. So it is the problem, it is not mentioned directly, but it is the problem to calculate RTH, right? It is problem to calculate RTH. Now as this problem contains a dependent source, which is a 2 volt source, this is the 2 volt source that is dependent on this voltage appearing across 5 ohm resistor. So we need to apply a voltage source, a battery source of known magnitude EDC, and that will inject a current of IDC, right? That will inject a current of IDC, having removed this 10 volt source from the network by short circuiting the terminals, right? We must remove 10 volt source first, then we must short circuit the terminals. So let us analyze the circuit one by one. So we have this current is IDC. Now one current is leaving from node X, let us say this node is X, it is this node, this current, and this current is also leaving from node X. So if we write KCL at node X, we can write KCL at node X. What we can write here is that IDC, that is the entering current, that is equal to, now this current is nothing but IXZ, let us say IXZ, okay. So this current is nothing but, we don't know till, okay, we don't know right now. This current, let us say this is IX ground, let us say this node is ground, or maybe Y, because all are same nodes. So let us say XY. So we have XY, this current, we don't know yet. So let us solve one by one. Again, so at this node, you see this KCL at node J, KCL at node Z, what is that? So this current is VZ by 2. This current is nothing but VZ by 2. This current is nothing but, it is VZ by 2, because this potential is Z and this is ground. So this current is VZ by 2, and similarly this current is VZ by 5. So basically, if we apply KCL at node Z, KCL at node Z, so two currents are leaving. So first current, as I represent, first one is VZ by 2, that is this current, and second current is VZ by 5, that is current flowing through this 5 ohm resistor, VZ by 5, which is equal to IXZ, which is equal to IXZ. And you know this, that is exactly written here. So basically, if we LCM it, then IXZ, that will be equal to 7 VZ by 10, which is written is equal to V. So if you solve IXZ, that is equal to 7 VZ by 10. Now this current, actually, you know, this potential is V, as it is mentioned, as it is seen, this is V. So therefore the potential of node Z is nothing but V. potential of node Z is V. So we can write Vz is equal to V. So from here we can write Ixz, that is equal to 7V by 10. Now next we apply KVL on mesh 3. KVL on mesh 3. Now let us mark the individual polarities. Let us mark individual polarities before writing. So we have a voltage source EDC, that polarity is upper plate plus, lower plate minus. And we have these 2 ohm resistors. We have considered current is flowing from X to Y, so that upper plate has to be plus, lower plate has to be minus. And the polarity of the dependent source as shown in figure or as indicated in the figure, it is upper plate is minus and lower plate is plus. So as per this polarity convention, you see this EDC, that is voltage source, and this dependent source are additive. So that is why it is written EDC plus 2V, EDC plus 2V, that is additive. With respect to that, these two, that is the voltage drop across this 2 ohm resistance, it is subtractive. So that is written 2 into, now this current which I initially mentioned and XY, that is written as IDC minus 7V by 10. IDC minus 7V by 10. Why? This entering current is IDC, this entering current is IDC, and this leaving current which is Ixz, which we have evaluated as 7V by 10. That is why it is written IDC minus 7V by 10. So if you solve, the left hand side will become EDC plus 2V, then right hand side becomes 2IDC minus 7V by 5. Okay. So this is one equation for you, equation number 5. Again, if you apply KVL at mesh 10, mesh 2, if we apply KVL at mesh 2, let us mark polarity. Let us mark polarity. So this is minus plus, that is the dependent source. So as per this polarity, so you see, so this V, that is the voltage appearing across 5 ohm resistor, voltage appearing across this 1 ohm resistor, they are additive. This dependent source, again these three are in additive. So we write okay, EDC as you can see. Why? Let me explain. So this voltage is EDC appearing across X and Y. EDC. So basically, since there is nothing connected between this X and this Y, so this EDC voltage will be appearing directly across this node and this node. So this dependent source and this voltage drop across 2 ohm resistor, these two will, if you add these two potentials or subtract depending on the polarity, of course it will be subtraction because they are subtractive polarity. So if you subtract them, it will give you a value of EDC across this terminal X and Y. So this will be EDC. Now with respect to this EDC, these two voltages are subtractive in nature. So this is VXZ. This voltage is VXZ. That is the voltage drop across 1 ohm resistor. This, and then voltage drop across 5 ohm resistor, which is V. So now what is VXZ? VXZ is equal to 1 into IXZ. 1 into Ixz, because it is current flowing through the 1 ohm resistance. What is the current? Current is Ixz. Now what is Ixz? Ixz is equal to 7V by 10. Ixz is equal to 7V by 10. So if you substitute EDC is equal to EDC, now Ixz is equal to 7V by 10 plus V. So if you solve this, you will get EDC is equal to 17V by 10. EDC is equal to 17V by 10. So this equation from equation 5 and this from equation 6, if you solve these two, then we will get, so from equation 5 you can write, you see, EDC plus 2V. Here it is 2V, right? So 2V you can write V is equal to 10 EDC by 17. 10 EDC by 17 equal to 2 IDC, then minus 7 by 5 into V. So what is V? What is V? V is equal to 10 EDC by 17. 10 EDC by 17. So if you solve this entire equation, so that is exactly, it is written EDC plus 2 into 10 by 17 EDC equals to 2 IDC minus 7 by 5 into 10 by 17 EDC. So if you solve this, you will get RTH. The solution is this. So RTH is equal to EDC by EDC by IDC, which is equal to, from this equation, 2 by 3 ohm. So with this result we can conclude that if RTH is equal to 2 by 3 ohm, and as per the Thevenin, as per the superposition theorem, if RL is equal to also 2 by 3 ohm, then we can conclude that maximum power will be transferred. Maximum power will be transferred. So this is the extension of a Thevenin's theorem problem. So with this, let us end this session here. So in this part we have discussed different, or we have rather solved different problems on Thevenin's theorem. Now one important thing you must remember, to solve any network problems, it requires a continuous practice to have the grip on the problem. Let us have, there is no alternative to this. You must practice continuously. If you can do that, you have a essence, you have the gut feelings that to analyze any particular complex network at a certain point of time, you can have knowledge, or you can have the essence that what should be written in this point of time. And that means whether now it is right time to write KCL, or it is right time to write KVL, or what should be done, in which manner the equation can be written. This essence or these feelings will come automatically to you if you solve the variety of the problems continuously. The one only approach to these problems, that if you solve these problems continuously, various problems continuously, then automatically you will be very confident and automatically you will feel the inner sense of that problem, what to be written at what point of time, whether it is a KCL or KVL equation and something like that. So I request everybody to practice at your own wish. So more practice will make more perfect for this type of problems. So with this I am ending this session here. Let us proceed in the next section with different with the remaining theorems and remaining topics. Thank you.